Okay. No, we're not there yet. Okay. This is very interesting, right? So there are many applications for electromagnetism. Remember that we discussed about electromagnets. So you can have a magnet go inside a coil. In this case, a voice coil in a microphone or a speaker, right? So there is an induction, and due to that induction, you have an AC current. So you can produce an alternate current by varying the magnetic flux. Because when you introduce a magnet, you see the north and south in there? Inside a coil, we are in some way emulating Faraday's experiment, where he had a primary and a secondary coil. And the idea was to produce a current, induce a current in the coil by changing the magnetic flux. And then that allow us to have a sound, right? So the voice coil and the speaker cone is the one on the right hand side there, they oscillate with the same frequency, because that's the thing about AC currents. AC current is a sinusoidal type of current, meaning it varies with time. It has an amplitude, frequency, and period. So it can be drawn or illustrated as a wave. A wave function illustrates AC current. You can use sine or cosine. Now, even though we're not going to do the math, it's important that you know that in particular. And that is because of how you generate AC currents, either by this model or by the spinning, right, by the generator, which we did, I believe, was way before, right? Here, right, with a waterfall. So the way we introduce electromagnetic induction is with a generator, where you have a coil or coils, and then you have the rotation. That rotation is measured in radians per second, the amount of degrees in radians per unit time is rotating. So that is the angular frequency, actually. So we can have that, and obviously that's how we know electricity and magnetism are, they relate each other, they interact only when there is motion. So a charge moving produces a magnetic field, a current also. Static charges do not, right? However, with electric fields, when we studied electrostatics, or when I introduced electrostatics, there is electric fields in static charges, non-moving point charges, right? So look at this concept now, right? The electric field can be due to a charged particle, and it will cause a force on a charged particle. An electric field induces a magnetic field when it changes. The same with magnetic field too. So this is basically how you relate electricity and magnetism. We normally say that a time-varying magnetic field induces a time-varying electric field by Faraday's law. Okay. So a magnetic field normally causes a force on a moving charged particle. An example would be a particle accelerator, a cyclotron, right? It's going in a circular orbit, right? And it happens due to an external magnetic field that is giving the particle a force. A stationary electric charge does not produce a magnetic field, only a moving charge. How do you reverse polarity? By reversing the current. When you guys do a lab in physics, well, obviously, and you can have a negative current, a multimeter like the one I showed you last class can give you negative currents. So the way you change it is by reversing the polarity. So you change the direction of the cables. That is actually important, although a negative current, if you take the absolute value, you have the value of the current. It's just that it's negative because of the direction. Sort of like vectors, if you think about it. A magnetic field exerts a force on an electric charge if the charge is moving. The charge needs to move to feel a force from a magnetic field. All right. You can make current in a coil by induction due to a magnet. If you connect it to a battery, of course, DC, and there it is, right? So 2 and 3 are both when the coil is moving or when the magnet is moving in and out from the coil. So all of the above for that. When the coil in a simple electric motor is turned by a crank, for example, right? Okay, in that case, a motor is a generator. It's basically the concept of generators in real life, or I believe also in video games, right? They show you that. When you're trying to turn on a generator and you have like a cord, you have a motor inside, that electric motor is rotating. So that is there. It's being turned. An electric current or changing electric field induced by magnetic. Yes, that is from Faraday's law, because Faraday's law states that voltage is induced and therefore a current when you have a changing magnetic field. If there is a voltage, there is an electric field. All right. So a changing magnetic field induces a changing electric field. And then we have the concept of transformers. All right. So a transformer is a very interesting concept, because even though, you know what's interesting, right, is that nowadays we still use transformers. Not like back in the day. Back in the day, I don't really remember seeing this, but back in my parents' house, they had a big black box. It's heavy. And when I read into it, it says transformer. So the way it used to work is you will plug in your TV, for example, and then the transformer will be plugged into the wall. Why do we do that? Because we are lowering or increasing the output voltage. All right? And the figure there is key to understand this, because the voltage is plugged into the AC generator. You have the input, one of the coils, and then the other coil. So why do you have more turns in one coil than on the other? Because, so let's stop here. Because in the coil, when you have the, by the way, AC symbol is like this. All right, and this is all connected to a coil. You can have maybe 3 turns in there, right? And then you have here the output. What we know is that this is the input, and that's the output. So what we know is that the voltage in divided by the voltage out is equal to the number of turns initial or in over the number of turns out. So if the number of turns in is lower, then the number of turns out will be lower as well, right? So what we are seeing there is that if I give you here, normally what you guys receive in your household is 120 volts. The number of turns in the input, it's normally, well, let's say 100 turns. Actually, not 100, that's too much. 10 turns. So this is normally for the output. Let's say you are, 20 years ago, you will buy a TV or a PlayStation or a computer from the US to take it to South America. All right? That will be very common. It's cheaper here than over there. So the voltage here is 120 volts. In South America, it's 220. So if you plug in the device from here over there, it will burn. It's too much voltage. It will burn the equipment. So we have to use a transformer. So the output will have to be 220 volts. So the question becomes, what's this N output? What's that? So the voltage, right? Like that. Probably better like that. The voltage input is 120 over the output, which is 220, is 10 turns over N out. So very simple, right? The N output will be 220 times 10 over 120. 0, 0, half 6, half 110. This is approximately 15, 16, 17, 17.3 tons. So the difference doesn't seem like a lot, but that difference is enough to correct for the voltage. Nowadays, the transformers are normally included in the device. Not in the device, but in the power charger. If you have a laptop and you take a look at your charger cord, right, the device that you use to charge the cable, normally it will have a battery, like not a battery, but sort of like a battery. Now for laptops it looks like a battery. For TVs, actually for TVs I don't think they do that, because for TVs they do models specifically for each country. But for your phone charger, there you are. Every phone charger nowadays can be used in many countries. because if you look at the specifications, it has a range from 110 to 240 volts. So you can plug your phone charger in South America. I know that because I do that all the time. You can plug it in Europe and Australia. Of course, the only problem is that they may have different, inputs, like the plugs, but it won't burn, right? Some devices they already have the transformer installed. Now I remember, TVs and video game systems, they do not. They do not. So what we normally do, Nintendo does it though. Nintendo does have, because they were clever about it. But I don't think Xbox or PlayStation does it. So normally they produce their own for each country. And the problem is that they are more expensive. So you have to be careful whenever if you're sending electronics overseas, take that in mind, all right? Phones are universal. Okay, so let's share again. And I think I show you that slide. Phone chargers, right? Transformers are found in different electrical appliances. All right. All right. Then you can also have applications of induction in a metal detector. All right. It's based on magnetic pulses. And how are they produced? By sending a current through a coil inside the metal detector. And then when the current stops, the magnetic field dies very quickly. This induces a current also in the coil because we are changing the field. This is how you monitor that change on magnetism, which is due to metals. That's how metals are detected, by magnetic pulse and a change in the current, and therefore in the magnetic field. And the pulses are detected by this metal detector. That's basically it. So I remember trying to build one of these. It wasn't successful. You can try to do one using Arduino. If you're Arduino, by the way, since we're doing this, there are a few things that you guys could get for at-home experiments. If you have kids, that would probably be useful. One of them is Arduinos. Arduinos are very nice microchips, and you can build your own circuits. Some of them have coils, some of them have diodes, potentiometers, resistors. So it's a very interactive kit. I think it's $25 per kit, last time I checked. Arduino Uno. Anyway, a magnetic field will be produced at some point in space if the electric field gets stronger. Yes, because it's changing. Gets weaker. Yes. Changes direction. Yes. You know what? This is like the acceleration. An acceleration is due to going faster, going slower, or changing direction. So that's how you can remember, right? An electric field, which is a force, it's a force field, gets stronger, gets weaker, so that means that you will have an electric field if a magnetic field changes. Either gets stronger or changes directions, all of them both. True or false? A transformer works with AC, but not, that's true. By the way, a transformer always, you know what? Because it's always plugged into households. Households do not receive DC. And the thing is that there is no point on using a transformer on an AC voltage, on a DC voltage, because it's constant. You can just change the setting and you reduce it. However, can you transform AC to DC? Yes, you can. And that was a very nice experiment we did right before the pandemic for science fair in the school back in March. We used a signal generator, which is an AC, but you can also buy an AC. Was it a transformer? Yeah, it was a transformer. It was not a transformer. It was a device that you connect to the wall and then you can have AC, obviously, AC current, and then you can connect this to a diode. Or it was actually I don't remember. It wasn't a diode. It was something. It allowed us to. It was like a electrical device where you will have an input and output, like a transformer, basically. There you are. And then we're able to change from AC to DC. All right, and you can see how the current gets constant by using either a multimeter or an oscilloscope, which, don't worry what an oscilloscope is. It's a device that we use just in the lab. Okay, so we were talking about this already and how we can use it. By the way, this principle of the coil and the magnet and the magnetic tape, it's also used in or similar in electric guitars. An electric guitar, by the way, you see when you play a note, you are creating a vibration, you are creating motion, you are changing, you are creating what? You can create a changing current, which gives you a changing magnetic field, which gives you an induction, which gives you an electric field, which you can actually get sound, just like you're seeing right now. Oscillations in and out of an electromagnet. All right? Which of the following does not use electromagnetic induction? The transformer does it, the dynamic microphone does it, the tape player and the speaker, they also, all of them use electromagnetic induction. All right. You can make speakers that do not use though. So I guess it will be one. You can have speakers connected to DC currents. DC. So both. You can have speakers that do both. So I guess number one will be the answer. A speaker can be used as crude microphone. Yes, but the quality is bad. That's more electronics there. All right. A speaker can be used as a crude microphone. Yes. The best way to test this is put your speaker next to another microphone, or vice versa, and you will see the sound quality there. Okay, don't worry about this too much. All right. What you need to remember from electromagnetism is induction, changing magnetic field, changing electric fields, and generators and motors. Okay, it's not very complicated, or it's not complicated, it's more conceptual. And obviously transformers, right? The equation that we did in the whiteboard is very important. All right. Before we go into this, because this topic is actually not that long or difficult, I want to show you guys the worksheet for current. Because current is also going to be in the exam. Week 8, the last week problems. So remember that for current, all right, for example, watts is the unit for power. And hours is time. But to get energy, you multiply power times time. Now, technically speaking, you should change hours to seconds. But if you look at the answer, they are all kilowatt hours. All right? So, 8 times 100 is 800 watts hour. But you want kilowatt hour. So what do? You divide by 1,000, right? It's 800 watts, or 1,000 watts is 1,000 watts is 1 kilowatt. All right, so 0.8 kilowatt hours. Now, why do we use that unit? Because that's the unit that we use in, that's what they use in electrical bills. All right. Now, if they give you the current, the resistor, and the time, how do you get energy? You multiply, you do the formula, current squared times resistance. Okay, so look, just a wiper for that. There are three formulas for power due to current, voltage, and resistance. The formula is, or the three formulas are the following. One of them is current times voltage. The other one is the square of the current times the value of the resistance. The other one is the square of the voltage divided by the resistance. All of those give you power. Energy is power times time. But you have to be careful with the units. Normally time is in seconds. All right? Now, if you have a current of 14 amperes and a resistance of 8 ohms, and you want to find the energy consumed in 24 hours, but you want this in watts hour or kilowatts hours. So the resistor, the current is 14 amperes, and the resistor value is 8 ohms. You want to find the energy in 24 hours. The energy will be I squared times R times 24. Power times time. 14 squared times 8 times 24. 196 times 8 times 24. That will give you the energy in watts hour though. Right? So if you use a calculator, I get 37,632 or 37.6. You can put here 37.6 kilowatts. Now, if you want to know the cost, you need to know the cost per kilowatt hour, which is 9 cents. So they tell you that current costs 9 cents per hour. Oh, kilowatt hour. So what I will do is I will multiply 37.6 times 0.09, and that will give me my value for the energy, which will be the cost, sorry. Wait, is that correct? Yeah, $3.39. multiply by 30 days, you can get approximately $90 to $95 a month, right? Which is probably the average for a household. Well, it depends, right? All right. So that's the only calculation that you need to know. There are more calculations that we can do in chapter 7 and 8, but they will get too complicated, okay? By the way, I will be teaching, I don't think any of you will need to take this, but next semester I'm teaching Physics 111 online though. So if you know somebody who is interested, you can always let them know. All right, I'm still planning to do a class even though it's online. So normally in Physics 111 is when we go more in depth on many of these concepts in terms of the math, right? Okay. All right, guys. So the last topic on these two chapters is electromagnetic waves. Electromagnetic waves, we studied them in astronomy a lot. In fact, I did apply some of those examples when we studied mechanical waves. When we did mechanical waves, I talk about a rope, like the ones that you can use in the gym, water waves, like in the ocean, and obviously sound waves. Now, the key difference between an electromagnetic wave and a mechanical wave or a sound wave is that an electromagnetic wave doesn't need a medium. An electromagnetic wave can travel in the vacuum of space. Radio waves, microwave, infrared, UV. What am I talking about there? I'm talking about the spectrum of light. An electromagnetic wave is a transverse wave. What is a transverse wave? A transverse wave. It's a wave where the oscillations are perpendicular to the direction of oscillation. But this wave is not just a 2D wave, like the one we did, like the ones we used in sound or mechanical waves. These guys are 3D because they have a combination of both electric and magnetic fields, but they both are perpendicular to each other, and the direction of propagation is perpendicular to both of them. So you have three directions: magnetic field direction, electric field direction, and the direction of propagation. Now, how can you produce an electromagnetic wave? Radiation. When you guys talk about radiation, a charge accelerating, and AC. So radiation is generated by a varying field, either electric or both, magnetic and electric. So an electromagnetic wave is a combination of these fields, but both of these fields need to be varying. They can be constant, right? If not, you won't have a wave. It will be just a constant. So you need to have a variation of this. So an accelerated charge is a good example. An AC generator is also another good example. Right? And there is your... Now, they don't show you the graph of the wave in 3D, but they show you the direction of both, the electric field and the magnetic field. But let's do this. Let me draw you guys an electromagnetic wave. So I will use the whiteboard for this because I feel like it's more, it will be better. Just that. So if I do that. Okay. To draw an electromagnetic wave, you need to be comfortable with drawing 3D shapes on a piece of paper. So I'm gonna give you the way of doing this, right? Normally, you will have your axis, but I'm gonna draw them like this now. So, from your perspective, you have here the lateral, the back, and the floor. It's like the corner of a room, right? And I wanna imagine there is like a oscillating charge or a generator in here at that point. So now I'm gonna draw the electromagnetic wave. Hopefully that will work. Okay, so look, you first have an electric field, like that. Right? I'll probably be more clear here. Like that. It's a wave. Then you can have a magnetic field. How do you draw the magnetic field? Perpendicular to this guy. They change the same period. So the magnetic field is like this. That's the amplitude of the magnetic field. The amplitude of the electric field is like this. They both are perpendicular. All right. The direction of propagation is like this. So perpendicular to both, right? You have the vector electric field and the vector magnetic field. So the propagation is perpendicular to the electric field and the magnetic field. What's the speed of this wave though? You know what? It's traveling at some speed. So what's the speed of that wave? If the electromagnetic wave is on vacuum, it doesn't matter what type of wave it is. On vacuum, the speed is the speed of light that we label c. And the speed of light is not infinite, it's large, but it's a constant, right? The speed of light in meters per second is, we round it to 3 times 10 to the 8 meters per second. Several experiments have been made to measure it, right? There's an experiment, the TCO experiment with a mirror and a light source. Now you can do it with a laser pointer. And there is an astronomical experiment using the eclipses of the moons of Jupiter. Regardless, even though it was a very rustic method, the method using the eclipses allowed to give us an idea that the speed of light was not infinitely large as it was thought. So it has some finite value. It's large, but it's a finite value. And that allows us to explain a few things. For example, that the light from the sun takes approximately 8.5, 8.4 minutes to reach us. Anyway, so just like the waves that we studied before, this guy has wavelengths has frequency and period. Frequency is the inverse of period. And amplitude, right? But the amplitude depends on which one you are looking at. You have the amplitude of the electric field and the amplitude of the magnetic field. And the particular thing about this wave is that the amplitude of the magnetic field is much smaller than the amplitude of the electric field. Yeah. The wavelength, as you remember, is the distance between two peaks or two valleys. All right. And it has periodicity. So clearly, right, you can tell what type of functions we use to model this. We use sine and cosine. Oh, there it is, speed of light. Yeah, magnetic field, electric field. The equation that we did back in mechanical waves in chapter 6 still holds. The speed of the wave is equal to lambda times frequency. But guess what? You already know the speed of light. So if I give you any frequency or any wavelength, you can get the wavelength or frequency in meters, of course. For example, of an FM radio. All right. Now, normally FM radios are in the megahertz range, right? 100 megahertz, yeah. So they have a high frequency. Now, the wavelengths are also sort of large, 3 meters, in comparison with the wavelength of light. The wavelength of visible light is in the order of 4 to 700 nanometers. A nanometer is 10 to a negative 9 meters. So you can get an idea. I wonder if they have the, oh, there it is. We're gonna get to that in a moment. So you will have a question where you have to do that. In fact, there's one on the whiteboard so you can see how easy this is. So I want to give you a random frequency, right? Let's say I give you, now in different units though. So give you in hertz, it's very easy, right? So let's give you a frequency. Let's suppose this wave in vacuum has a frequency of 80 megahertz. I want you to find the wavelength. Here is the formula. C equals lambda F. C is this guy. Lambda is what you want. Frequency is 80 megahertz times 10 to the 6. So it's 1 million. So you will have 3 times 10 to the 8 divided by 8 times 10 to the 7. This will be 30, because 7, 8 minus 7 is 1, 30 divided by 8, which is approximately 3.5, yeah, 3.5, 3.6 meters. Okay? Like that. This is one of the main slides on this section, because here is where you see the electromagnetic spectrum as a whole. And here is where we have the radio waves, and here's where you can see the microwaves, the infrared, the ultraviolet UV, X-rays and gamma rays. And some of the applications, right? Radio waves for radio antennas, microwaves also for cooking, ovens, infrared, there are controls based on infrared, right? Although you can also use them in medicine, right? Ultraviolet, normally we use them for, I believe, tanning salons. Actually, now that we're going through all that horrible thing, right? UV can be used to clean an environment. You can use UV light to kill viruses, like the flu or this horrible thing right now. You can use it, UV light, but you have to expose it for at least a couple of hours, I believe. So let's say I have this lab right now, right? I can put a UV lantern, I leave it the whole night, I come, and the environment will be totally clean, for sure. It kills viruses. It's probably something that they're going to be using in the future, by the way. Airplanes actually are pretty safe. Believe it or not, they are. Bars and restaurants, they probably will have to eventually. Yeah, maybe. And then X-rays, and gamma rays as well, very energetic. So as you go towards the right, you get more frequency. More frequency is more intensity, more energy, but less wavelength. Look at the wavelength at the bottom, 10 to a negative 14. Very small. As you go to the radio side, you get larger wavelengths. All right. You know what's a particular thing about this graph? Look at the very narrow visible light spectrum. It's tiny, right? When you think about it. So what we observe, even in optical telescopes, in astronomy, you are only looking at a very narrow part of the spectrum. So there is a lot of information that we are missing in the other wavelengths, right? I mean, you can look at a picture like this, but if you take a radio picture of that, you will get more information like the radio contours. For example, to investigate black holes, AGNs, quasars, the center of galaxies, right? You need to observe them in different parts of the spectrum. And then you also have, for example, the Chandra X-ray Observatory that we use to observe black holes. There is your IR transmitter, by the way. You don't need to memorize this, the range of values of frequency or wavelength. However, as I said before, visible light has a range between 400 to 750 nanometers. All right? I don't like that table, actually. It's not very nice. Because they give you the units like that. Nah. The best way is to remember. And the thing is that it's a very narrow range. 400 to 750, it's not much. But it's enough to have this variety of colors that we see, right? A color is basically an emission of an electromagnetic wave, guys. Different lambdas, different wavelengths, you have different colors. By the way, you know something that is interesting about, oh yeah, there is your UV lamp in there. There it is. All right. So actually, UV lights in that case, as you can see, they can be used to attract nocturnal insects. Actually, some birds and insects can observe UV light. You probably have heard about this, right? It's in biology. So, and that's what I was looking at. UV lights, UV lamps can be used to sterilize workspaces. All right. So barbers and salons actually may end up doing that. Who knows? It's expensive though, so it's not like it's cheap. Then you have X-rays. So now is when you can apply some of what we did before. We have a DC voltage in there, and you can have electrons being accelerated due to the voltage, and then you have a target. depending on how fast they move, electrons can emit X-rays, like that. All right? There is something called scattering of particles. You know when this happens? In the accretion disk of black holes. So when you have a black hole, it's not just gravity and tidal forces attracting an object and destroying it, disintegrating it and sucking it, right? It's also enormous magnetic fields. And they normally have a shape, not exactly of a toroid, but they sort of resemble that, like a donut. And the thing is that you have particles moving at relativistic speeds, so very fast. And what we can have is that those electrons can be moving so fast that they can collide with one another. So normally what you can have is radiation coming or radiation in the accretion disk due to matter falling into the black hole. And if they collide with a high-speed electron in the accretion disk, that radiation can be bumped into actually an X-ray. We call that the inverse quantum scattering. I remember that very well because that was the topic of my research. This was in 2011, 2010. We were investigating the black hole at the galactic center in the Milky Way. And some of the observations led us to think that was going on in there. All right. Okay. Medical imaging, X-rays, and then gamma rays can also be used for astronomy, but also in medicine. For example, applications for medical or medicine to bombardment of cancerous cells. Okay, let me see what else have here because I wanted to get to this actually. Okay. So what you're seeing there right now, guys, is what we know in astronomy as the black body radiation. So actually we're getting now into a bit of the quantum part because normally we use this example for quantum mechanics. Something that you guys should know is that classical physics, when we study the radiation coming from the sun, for example, right? We know that the radiation, the power of the heat by radiation is proportional to the fourth power of temperature. So the intensity up until the ultraviolet section here is normally like this, like a parabola. But look what happens. It reaches a peak and then goes down. This is called the ultraviolet catastrophe. Classical physicists call it like that because that was the tick point when they realized that classical mechanics, classical physics, was not enough to explain certain phenomena in nature that you had to explain using quantum mechanics, photon, radiation. In this case, the Planck law or the black body radiation law. You know why we use this? We use this to characterize the intensity and temperature of any body that has some temperature. The sun, a planet, a comet, we can use this to characterize that. All right. For example, just so you know, the sun, the light from the sun, when we do the black body radiation, it has a peak around the green. So, in some way or form, the intensity of light that governs the sun is the green part. It's not like, it doesn't mean that the sun is green. The light from the sun is yellow, it's white. It looks yellow because of refraction, by the way, and the atmosphere. But it's actually, the light is yellow. It's a combination of all the colors of the spectrum, right? And then why is the sky blue, for example, right? It's because of scattering. So when the light of the sun gets to the atmosphere, it scatters, interacting with the atoms in the atmosphere. The scattering is more effective in the blue section and less effective in the red section. That's why. That's the radiation based on classical physics, by the way. All right. The Planck law is different. It fixes this equation. But again, don't worry about the equation, right? It has an exponential form there. It's very complicated. But from this, we get this, by the way. This is called the displacement law. It's how you relate wavelength and temperature. Wavelength is in meters, temperature in kelvins. All right. Something that I always tell students is that the temperature in science is not measured neither in degrees nor Fahrenheit. We measure temperatures in kelvins. All right. Now, obviously, the larger the intensity, the more is Q. So, the more is Q to the left, the curve is, the less wavelength we'll need to find the peak. Right? And that makes sense with these guys. The frequency, the wavelength and the temperature are inverse from each other. If the wavelength increases, the temperature decreases. And the temperature is a factor for power. And what is intensity? Intensity is power per unit area. So it makes sense, right? If the power goes down, the temperature, that means that the temperature is going down. That means that the wavelength is going up. Here. Less intensity, right? The peak. If the wavelength goes down, the temperature goes up, the intensity goes up. Alright? Don't worry about the equation. We're not going to be testing that. It's just for you guys to know. The same with this. And these are some of the applications. We use this for stars to model their spectrum. So we can use this black body radiation to model the spectra of stars. All right? And why do we need that? Because by knowing that, guys, we know the peak temperature of a star. And by knowing that, we know the surface temperature of a star. And we can compare that to the spectra of the sun, because we know it perfectly. The spectra of the sun peaks at a temperature of around 6,000 kelvins. So actually, let's do the exercise. What will be the wavelength then for the peak of the sun? Let's put a calculator here. So the temperature of the sun, the surface, is 6,000 kelvins. So if I do 0.0029 divided by 6,000, I get that. That's approximately 483 nanometers. Because if I multiply by 10 to the 9, I get 483 nanometers. Alright, then we go, I'm not going to use the one in the slides. I'm going to use this one. I'm going to show you. So you are in between here, right? The peak. So that allows us to find what's the peak wavelength for the sun in this case. Right? In meters, of course. So that's why I have to convert to nanometers. Right? If you have a star like Vega is around 10,000. Let's see what we get. 0.029 divided by, oh yeah, of course. And then times 2,900, so that's less than that. So that's 2,900 nanometers. Normally, Vega will be in the whitish, it's white, it's very white, very bright spectrum. In any case, we can use this equation to find where this peak fits with that maximum intensity. All right. Okay. Something that I didn't talk, guys, is the Doppler effect, and with that we're gonna finish. All right. The Doppler effect also happens in light. What was the Doppler effect? You remember that was in the quiz, right? When sound intensity changes due to the moving source. So now let's give you this picture. Imagine this star is moving away from us. The intensity of light will decrease, but the wavelength will increase. That's the Doppler effect for light. When the moving source is moving towards or away from the observer, that's when you have the Doppler effect. And the main difference is what you have in the equation. Now you don't have the speed of sound, now you have the speed of light. So the wavelength and the frequency, they both change as a factor of the speed of light and the velocity moving away or towards the observer. Okay? Alright guys, so that's it. What we're going to be doing is the exam on Tuesday, chapter 7 and chapter 8. Alright? And then on Thursday next week, I will do a brief introduction to the next chapter, which is optics. And then, well, you know, the final exam is Tuesday the 15th. I will try to prepare by next week, besides your exams and your quizzes and the worksheets. Actually, guys, to be honest, you have all the material needed to study for the final already. All right? With exam number 3 and the worksheets and the quizzes, you should have everything. But I will try to get you at least a study guide of what you should focus on from each chapter. All right? As I said, all of you guys are going to pass. I'm not worried about that. I just want you guys to get the best out of this. Please do the course evaluation. Be honest about it so the college can know what changes they need to apply for the remote section. All right, guys? All right, guys. Take care, be safe, and I'll see you guys on Tuesday, okay? I will send you the link for office hours between tomorrow and Saturday, all right?
Okay, thank you, Professor.
All right, guys. Take care. See you later. It's 5 to 7.